Yeah, my name is Ilona Glatt. I'm a business manager for battery applications and also for the hydrogen applications, which is fuel cells and electrolyzers. All experts, hydrogen experts from the Math2Market would like to welcome you in this session, of course. Some of them are here in the back. And then we also have Arne here. And some of them can't attend this session because there are parallel sessions and we have to split up a little bit. But if you have any questions, you can ask any of them and they will be happy to answer you or to guide you to the right person. Not only through the session, but anytime. I already said I like discussions, and that's actually what this is all about. I mean, it's about you. You are making this event very special. And it's about your applications, your research, which is important to make this event a success. So, and special thanks to the guests who have the furthest to travel from Eastern Asia, from Japan, and also from Korea. So especially thanks to the speakers. We already had these speakers in the plenum session, and it was really, really interesting talks. Maybe we can have a little bit ongoing discussion about the talks later on. So thanks to Kato-san from Toyota, and also thank you to Matsumori-san from Honda, and also, of course, to our partners from Trinity and from SCSK, that you always come to our events. Thank you, and of course, to all of you. In the next 2 hours, we have a very interesting program. We start with a welcome, which is already over. And next, I will guide you through some hydrogen energy applications that you can do in GeoDict, or why would you use GeoDict for research in this area. And after that, we will have a talk by our Deputy Head of Development, Sven Linden. And he will give us an update on feature requests which were handed in by clients in the hydrogen business. And he will just tell us what is the status of these requests. Have they been slotted in? Are they working on it actually? What is the plan with this feature? And this will be followed by a discussion. We can already have the discussion during the talks, but if you there's a slot for it, so that there is time for discussion. So that's the important point. And then we have a short break where you can follow, go on with the discussions if you like. After the break, we will have 2 live demonstrations. The first one will be given by Jürgen Becker, who is the head of our support team. And actually, he started in the beginning, well, 15 years ago, something like that, started with the hydrogen applications in GeoDict. So he's kind of the pioneer for this kind of applications. And he comes back to his roots today and give us a live demonstration of how you can calculate relative permeabilities in a compressed PTL. And after that, we will have a live demonstration of a new feature, which is the unresolved mercury intrusion experiment in an MPL and GDL compound, because one is resolved, the other one can't be resolved if you have a reasonable structure size. And there's a live demonstration given by Arne Jakob, who is the deputy head of our projects team, and he will just guide you through how to use that feature. So I will start with the applications in GeoDict for the hydrogen applications. And we've talked a lot about, heard a lot about GeoDict 2025, which is new and out now. And maybe you're asking yourselves, what does that mean for me as a hydrogen researcher? Yeah, I will answer that question, but not only for GeoDict 2025, but also for GeoDict in general. To do so, let me give you an example. One of our clients once said, in the 10 years since we started using GeoDict, the cost of our fuel cells has been reduced by 90%, the weight of our fuel cells has been reduced by 50%, and the performance stayed the same. So what does that mean? If you follow on with an example, just imagine we would be talking about the Mirai. That's just an example. I invented that. And I have some numbers taken from the US Department of Energy from 2016, which is almost 10 years ago. we imagine we have an annual production volume of 50,000 fuel cell stacks, and for this production volume, the MEA assembly, the membrane, GDL, MPL, and catalyst layer together is roughly $12 per kilowatt in production costs. So if you assume that, and you assume also the power of a Mirai fuel of the fuel cells in a Mirai of 128 kilowatt, the production cost for the MEA for one Mirai is roughly $1,500, and the yearly production of the Mirai is 30,000 per year. So with the 90% reduction in production costs, we would save 40.5 million per year. So that's just an example, of course, but to give you an idea, I think it really serves well as a nice example. So why are we here? If we want to decarbonize our industry, electrolyzers as a green hydrogen, as a green source for hydrogen, are really important. They are vital. Hydrogen is needed for several parts in the industry, very important ones. It's needed for oil refining, which is a little bit of an irony, but it's true. You also need it for fertilizer production and for steel production, and also for the cement production. For all of these parts, the hydrogen is needed. And currently, the hydrogen comes, well, currently 2 years ago, almost 3, 99.1% of all the hydrogen produced, even more, is from fossil fuels. So green hydrogen is only 0.1%, while blue and gray hydrogen, so the fossil fuels, is all the rest. And if we want to decarbonize our industry, it's obvious that that can't stay that way. What we do want to have is something like that. That would be nice, right? And if we do so, we don't really need the oil refining in that amount, at least. And we could replace that by fuel cells to ensure the energy grid, so electricity for everyone. So why isn't that the case already? That would be really cool, so why not? Yeah, the answer is very easy and very hard to solve. The gray or blue hydrogen costs much less in production than the green hydrogen. So less than half the price. So what we need to do is to lower the costs, to close that gap between the costs for these two types of hydrogen. And one way to lower the costs would be to improve on the performance. I know that's not the only thing that needs to be improved, but it's one part in the puzzle, improve the performance of the electrolyzers. And the question is not why to improve the performance, but how to improve the performance. What can be done? You can imagine the performance of the electrolyzers, but also for the fuel cells, also true for the fuel cells, is determined by transport processes inside of the MEA assembly. So we have to transport electrons, we have to transport gases, and we also have to transport water. If that's true for the electrolyzer as well as for the fuel cell. And the network for the transportation needs to be well organized, like in a city. If you haven't it well organized, you will get traffic jams and obstacles, so the transport will not work smoothly. And this is how the performance of the fuel cell can be optimized, by optimizing this kind of pathways in the MEA assembly. And this is where GeoDict can be of use. What you do afterwards to connect the microstructure properties or the transport properties that you determine in the microstructure to the performance is you usually have a 1D performance model, or maybe 2D, but a larger scale. And you need input parameters to run that model. And these input parameters at least partly depend on microstructural properties. And what was done so far is, or often done, is these parameters were roughly guessed sort of educated guess, of course, but in fact, it's more or less guessed. And with GeoDict, you have the opportunity to calculate these properties and connect them to the microstructure. And if you change the microstructure, these properties will change, and thus the performance that you get out of your performance model will also change. And during the next minutes, I would like to show you a few examples that you can use to connect the microstructure and use or calculate the properties of the microstructure, which you can then later on use as input parameters for performance models. The first of these examples would be to calculate the porosity and the pore size distribution of a microporous layer or a catalyst layer. They look very similar for analyzing the porosity or pore sizes. That works the same way. The next point would be to calculate the electrical conductivity of a gas diffusion layer. Yeah, we also have to transport the electrons through the gas diffusion layer to have a driving force for the electrolyzer or for to actually operate a fuel cell. And then the third example is probably the most complicated one, most sophisticated one, is the transport of the gases and at the same time of the water. And here we do have, in this entire session, we do have three examples. One is an example for material design of a GDL, which is here. You can see this icon that should symbolize that we have a real design study here, while the other ones were just for observation. And here we have a design of the material. And then in the last 2 points, I will just motivate the live demos that we have after the break and just explain why would one like to do that. The one was the permeability of the PTL, which is compressed by the bipolar plate. And the second one was the diffusivity of the GDL-MPL compound. I think we don't need that schematic, and we'll skip over that, but just to visualize where are the parts where we are talking about. And there's one thing what we need to have a look at all of these examples. We need to have a structure. We need to have something that we can work on. And what we do here is we have a realistic digital twin of a real material in the digital world. So it's just a copy, so to say, in the digital world of the real material. And how do we get that? Let me show you a little bit how you get a structure into GeoDict, which we then can call a digital twin. So the most straightforward way to get there is you would have a 3D scan. In this case, you can see a micro CT scan of a gas diffusion layer of a fuel cell. And if you scan it, you get gray values from the CT scan, and you can import this into GeoDict, and every gray value will become one material phase. And then you can reconstruct it in 3D, and you have a representation of the real material in the digital world, which you can already call a digital twin. So remember, if you have a digital twin like that, you have an exact representation of your material in the digital world. And in the case of the GDL, the individual fibers are exactly those as they are in the real world. And they have the same location, same thickness, everything same. And the properties on the macro scale are identical to the original material. For example, you would have the same permeability of the material. That would be a digital twin. Then we have a concept of a statistical digital twin, which is very similar, but not the same. With a statistical digital twin, you would have a digital representation of another part of the material. If you look at this image here, you have a carpet, and we have two different patches of this carpet. You would have the fibers in different locations. They would have maybe different thicknesses, the individual fibers, and you But in the statistical sense, you would have the same properties. It would have statistically the same fiber distribution, fiber length distribution, thickness, curliness. So you would end up with the same properties on a macro scale, like, for example, the permeability. So if we want to do material design, which is what GeoDict is really good at, we need the statistical digital twin to be able to alter the material. For example, say we want to have a different fiber length distribution to end up with different properties on the macro scale. As long as we have the same properties on the macro scale, we didn't do any designing, right? So if we want to do designing, we have to alter the material. And this is what we need a statistical digital twin for. In GeoDict, you have several options to create this statistical digital twins or structures in general. For granular structures, we have options, and also for fiber structures, and also for sintered structures, which would be valuable for the SOFC fuel cells especially. And then we have some options to make it a little bit easier to create realistic structures. For example, we do have an agglomerate generator, which creates these kind of agglomerates that you can see on the bottom here, so like these here. And you can use these agglomerates and put them in into a volume and generate a structure which is constructed out of these agglomerates. This is very helpful if you want to create, for example, a catalyst layer, which is done here on in this example, because a catalyst layer consists of this kind of agglomerates. And then you have usually covering of ionomer, which you can add later on in platinum particles and so on. But this kind of agglomerates gives you the typical pore size distribution that you have in this kind of layer. So you have large pores, you can see, for example, here in the scan, but you also have these smaller pores in between the particles. And it's much easier to achieve if you have these agglomerates to start with. That's another thing that we already heard about in the plenum session, the 2D to 3D app, where you can use 2D scans to get a 3D structure. I was actually impressed by the 3D TEM scans. But if you have TEM only in 2D, that's a different thing, of course. Same for FIB-SEM scans. FIB-SEM scans are very difficult to get, especially for the micropores layer, or even worse, the catalyst layer, because they're very, very small particles and it's mechanically not very stable. So if you want to have a good image of that, I have never seen one, which is actually one of the reasons why we started with the SOFC cells for the 2D to 3D app. Now it's also working for battery structures, and it's also working for fiber structures, but we're still looking for a really good scan of an MPL or catalyst layer. So if you have a really good scan of an MPL or a catalyst layer, you would be very interested to work with you on creating or improving on the 2D to 3D app using that kind of scan. So please let us know. So now we do have a realistic digital twin in the digital world. We can start analyzing that. So let's start with an example of the pore size analysis of the micropores layer or catalyst layer. Here on the left-hand side, you can see in gray the structure of a micropores layer. And on the right-hand side, we have a graph which you also get from experiments of mercury intrusion. So you get the pore size distribution, or the pore sizes. So you get the pore sizes on the x-axis, while on the y-axis you have this rather cryptic measure for the amount of pores that you get for this size. And the exact same graph you get in GeoDict if you run a mercury intrusion experiment. And then you can compare this with the experiment, or the digital experiment with the real experiment, and see, does it fit? If it fits, you're probably fine. And you can go one step further with the simulations, because with the mercury intrusion, you only get the throats of the pores, or the sizes of the throats. And for the transport, it's also important to know how big is the pore inside, so the pore body. And this is something that you can get with GeoDict. also hidden pores, so inside of the material. We had that in the plenum talk earlier. And this is something that you can use GeoDict for. And once you have validated your structure using experiments and digital experiments, you can rely on that and go one step further and use things that are not available in the experiment itself. What you can also do in GeoDict is visualize the pore sizes in 3D. So here you have in 3D in color the size of the pores, and you can just see how big is the pore at that I'm just currently looking at. For example, this pore is in red, so that means I have a very big pore here. Here are very small ones, they are blue color coded. Yeah, so you have two options, either reproducing the experiment or even going one step further. So you've seen the porosity analysis, and now go to the electrical conductivity of the GDL. What you can see here is in gray gas diffusion layer of a fuel cell, and you can calculate the electrical conductivity or the electrical conduction of this structure, and you get, for example, current densities in 3D, and you can see if you have any problematic areas, like for example here in the red ones, or here in 2D. You can also analyze it and slice through and see a little bit more in detail where there could be any bottlenecks for transportation. So let's move on to the most difficult task, so to say, the gas diffusivity or permeability of the electrodes, depending on the water saturation or on relative values in any case. We will start with the materials design. So it's a design study which has been done quite a few years ago of a gas diffusion layer. I think it was done by Jürgen Becker. So if I tell something wrong, please correct me. It was, I think in 2009 it was done. There will also be a citation later on. So we have the GDL here, and between the gas channel and on the bottom we do see the microporous layer. And in this study, the assumption was that the water which is generated enters in this compound or in this substrate always from the bottom, from the microporous layer in a liquid state. We've seen earlier on in the plenum that this is not always the case, probably never. But for this study, it was assumed that it is the case. You could also assume different or more complicated ways of how the water enters into that layer. But for this study, it's not the important part, actually. So we'll leave it with that way, and we'll start saturating that layer from the bottom. The idea here is, we can just have a look how that saturates. So we have the water entering from the bottom and saturating the gas diffusion layer until it's more or less completely filled. So the idea behind the study is now to do some microstructural design by punching holes into this gas diffusion layer. And as we have a very hydrophobic structure here, the water will presumably start forming or entering into the big holes which have been punched first. So leaving the smaller pathways open for the gas diffusion or permeability. So let's see how the saturation looks like. So it starts at the same location. And you see, okay, at least qualitatively, that works. We have filled the holes first. The punched holes are filled with water while the rest is still open for the gas transport. Does it also work qualitatively? Well, let's have a look at that. Wait a second. If we look at the graph here, we have on the y-axis. On the y-axis, we have the saturation with water in percent of the two GDLs. And on the x-axis, we have the pressure that is needed to get the gas through the structure. And if I let the video run, we can see that for the perforated GDL in red dashed here, we get a different graph than for the default GDL. And in the typical operation level, it's actually a little bit wider than it's shown here, but more or less. So in the typical operation level, we see that we need less pressure for the gas to go through at the same saturation level than for the non-perforated GDL. So in this study, the structural design, the material design worked out. The water fills the perforation first, and it leaves the smaller pores for the gas transport, allowing for higher permeability at the same saturation. Yeah, we have already seen the plenum talks, so we can refer to that. And this was the real world. I mean, this is a study which is done in a publicly funded project, and you're doing the real research, so for real applications. Now let me show you a little bit what the permeability of a PTL in a compressed bipolar plate is good for. We're talking about electrolyzers now, but it would be also true for fuel cells if you look instead of the PTL at the GDL. So what you do during production is you press the PTL and the gas channel together. And while this is pressed together, the PTL is compressed mechanically. You can see that on the image here. This is the gas channel, or one of the gas channels. And during the production of the electrolyzer, it's pressed into the fiber structure of the PTL. And we do get the compression then in the middle of the gas channel. So here we have less compression than on the outer side. And if we want to go into a performance model on a higher scale, we need to enter a permeability value. And the permeability that we get from the relaxed structure is different than the one that we get from a compressed structure, of course. The trouble is if we measure, or if we image the PTL with a scanner, it's usually in a relaxed state. So if you use this image of the relaxed state and calculate the permeability or the diffusivity of the structure and enter this into the performance models, it will probably not be the value that you have during operation. So if you want to have the value that you need for simulating operation conditions, you need to use the compressed structure. And this is what Jürgen will show after the break, how you can use GeoDict, or in this case ElastiDict, to compress the structure in a realistic way and use it for performance models as an input parameter later on. So the last example I want to talk about is related to the last task in the session here, which is the mercury intrusion curve that you get from the compound of the fibers and the microporous layer. So why would you want to do this? Well, scans of the microporous layer or catalyst layer are very hard to get. Already had this topic. So what you usually do if you want to have a scan of this compound, you scan it together with the GDL. And then it's usually not resolved. So the MPL, is not resolved, or you can't really resolve that. So what you can do in GeoDict now is you assume a porous medium for the microporous layer, the one here on the bottom. So for each voxel, you have pore inside as well as solid material. And you say, okay, my porosity, I know that, can assume that. And then you can calculate the mercury intrusion for this entire compound. And you get then the analysis for this entire structure. You can use that again for going into performance models as an input parameter. All right, so that was what I wanted to show you as an introduction to this session. The most important thing is the microstructure directly influences the performance of the fuel cell or of the electrolyzer. And GeoDict can help you to design that microstructure in a fortunate way. And with that, I would like to thank you for your attention.
Okay, thank you for the introduction. My name is Sven Linden. I'm the Deputy Head of Development at Math2Market, and I'm responsible for different solver technologies you have available in GeoDict. And today I'm going to talk about the status request, or the status of different feature requests. As Ilona already mentioned, last year we had a meeting with a couple of clients, and so they prepared feature wishes, features they would like to have in GeoDict. And during that meeting, the features were presented and discussed. And today I want to give like a status update about which features may be implemented in the upcoming GeoDict version, and what is already possible with GeoDict 25, which is available today. So here you see the different features. I cannot talk about all of them today, so I will concentrate on a few of them, but I would just want to briefly mention them. So we have feature requests about to have a GeoApp to create a multi-layered structures. For example, here a fiber structure with different layers. One request was to have like more validations for the different modules. The one that you see here in the image is GIC, and for example, to have a better user interface for unresolved two-phase flow simulations. Other feature requests were, for example, to have an improved mesh export, to have more features and better two-phase flow simulation, to be able to simulate gas bubble transport, and also to predict the performance of fuel cells, and and 2 to 3D, but for catalyst structures. So I will talk about 4 different topics, and one other topic will be covered by the next talk by Arne. So the first feature request I want to talk about is about two-phase flow, and here the request was to have like two-phase flow simulation to compute relative permeability, but with a different slip length. So the request was to have a different slip length for the flow simulation. To shortly give an overview what a slip flow is about. On the right side you see a velocity profile. On the top you have a flow channel. On the bottom you have some solid obstacle, and you have a pore solid interface. And usually when you do flow simulations, you assume that you have no slip at the interface between pore and solid, and that means you have no flow into the solid, but also tangential to the interface you also have zero velocity. But when you have slip flow, you can have a tangential velocity which is not zero. And usually you use this kind of boundary condition if you have, for example, like thin gas, and if you have small pore sizes. But it seems to be also important in fuel cells. And how can that be? So on the right-hand side, you see an image from a paper. Here you see a flow channel with a water droplet, and you have airflow around this droplet, and you see that so the droplet is not moving. It's stationary. So the interface is fixed, but you see that the airflow deforms the droplet a little bit. So you have different contact angles before and after the droplet. But what happens now if the airflow is fast enough, you get like a circulating flow in the water droplet. So on the right part of the image, you see like a circulating flow inside the droplet, and this leads to slip flow like a boundary condition at the interface between air and water. And what you can currently do, you can like emulate this kind of feature with GeoDict and FlowDict. So what you can do is, for example, you do a two-phase flow simulation with the capillary pressure command, and then you get a sequence of different water and air distribution. And now you're not using the relative permeability command in GeoDict, but now you go to FlowDict and you compute flow in a FlowDict. But before you do this, you can use the dilation command in a process geo, and you dilate. For the example from the slide before, you dilate from the air into the water and do then the flow simulation. And this emulates slip flow behavior between air and water, but you still have no slip between air and here in this case the fibers. So you can already do emulation of this boundary condition. What we plan to do in the next GeoDict versions to allow that you can specify different slip length for the different phases. So this we can do in the flow solver. It's not available yet, but this can be implemented, and it may be implemented in GeoDict 26. Okay, so the next feature request is about improving the mesh export. And yeah, so like the request was to have like more stable mesh export to be compatible with other simulation software like COMSOL or ANSYS Fluent or Abacus. And yeah, this is important because customers maybe already have like a software environment, and they want to use their own simulation software, but they want to use the structure generators from GeoDict. And this can be sometimes difficult because meshes can be quite big with a lot of triangles, and our software then have a hard time to import and mesh it to use their simulation. And also sometimes it also happens that with importing fails, maybe because of self-intersection of the mesh. If you do like coarsening, you can introduce errors. And yeah, so here we want to do major improvements, and this is scheduled, and we are already working on this. So in the last month, also workers started to do improvements here. So we want to improve remeshing algorithms to decrease the number of triangles, but preserve high quality meshes. And especially, and this is important where two materials touch. And so we will do more work on this to make it possible that the exported meshes are better compatible with our simulation software. Another thing we want to do is to remove the dependency from a cut look. So if you want to export a mesh in the so-called step format, you have to buy another license, a cut look license, and this makes it more complicated for the user because you need a GeoDict license and a cut look license, and yeah, not so nice. And yeah, here we want to remove this dependency and replace cut look by something else. What else I cannot tell you now, but we want to remove it and make it easier. Yeah, and of course other improvements, reducing runtime and memory and so on. So now we come to a different topic, to fuel cells again. Yeah, I think you have seen this image this morning already. So for me, the battery has similarities to batteries. So you have the anode and the cathode side. Hydrogen flows through the anode side, and some parts of it will lose its electron and travel as protons through the proton exchange membrane. And on the cathode side, it will merge together with oxygen through the oxygen reduction to water vapor. For research, it seems to be that the cathode side is more interesting because here you have water production, and water can condensate, and this makes it much more complicated. And so research happens on the cathode side. And research questions are, for example, is always enough oxygen available for the oxygen reduction equation, because the performance depends on this. How well is the water transported out of the cathode side? And what about the platinum? So the oxygen reduction happens at places where you have platinum, which is a catalyst. And how well the fuel cell performs depends on the distribution of platinum, and how does it influence the diffusion of oxygen. So what you can already do with GeoDict 25 is you can simulate the transport of oxygen and the transport of water vapor. So not water, but water vapor. Tomorrow, my colleague will give a talk about our new transport solver, which is available in GeoDict. And this solver allows to transport concentration on a given velocity field. And we can use this in combination to simulate this phenomena which happens here. So if we assume that, for example, we have air, we have just air, we have as a solvent, we have oxygen and water which stays as vapor. And if we assume we have enough of protons and electrons, and if we assume, for example, here also constant in temperature and pressure, and here we also assume that the micropores layer and the catalyst layer are not resolved, we can do the following. First, we run a flow simulation through the fuel cell, and then we use the transport solver. So we transport oxygen, and then we transport water vapor. And so we transport concentration with a velocity, and then between different time steps we use some kind of update rule, and this can be implemented in Python, and you can very easily then use a simple update rule to implement the oxygen reduction equation. And so iteratively for each time step you transport oxygen and water vapor, you do your reaction in Python, and so with that you can do like an evolution. And here in the video on the right side, you see the evolution of water vapor over time. So my colleague will give a more detailed overview about this new solver tomorrow. And using this technology, we think we can also do more. So if we have a model of a catalyst layer, we may also be able to do like a more detailed simulation. To also do maybe like a multi-scale model where we do simulation on the resolved catalyst layer and use this result for like on a simulation on a bigger scale. So okay, so the last topic will be about 2D to 3D. So as you've already heard, we have two GeoApps in GeoDict 25. With one, you can create statistical digital twins, so for fiber structures, and we have another version designed for granular structures. And we have tried it so we have tested if we can also model a catalyst layer. And here on the left side you see a 2D image of a catalyst structure. Actually, this is from another GeoApp in GeoDict to create a catalyst structure. We have used one slice of it and use the GeoApp and to test if it is possible to use it already as it is to generate a fully digital twin of a catalyst layer. And in the center you see the result. It's not ideal yet, but you can already see that it's similar. The reason why it's not yet ideal is because you have like an internal generator so you have a model, a generator model, as Eric already told, and yeah, to have like a better match between the input image. Some more work would be needed to tune it, so to change the generator model such that it is able to fit better to catalyst structures. So to do more work here, we need also like real images. So this would be like the end of the presentation. So some of the requests are partly possible, and some are planned for future GeoDict versions. So that would be from my side. Thank you for your attention and for the discussion.
So we can start now with a live demonstration. The beginning, I think, is not live because you have some introductional slides to that. And I already gave the motivation. So I think you will give your own motivation soon. And so I hand over to Jürgen Becker, our head of the support team.
Yeah, thank you, Ilona, for the introduction. I came to Kaiserslautern after I finished my PhD in mathematics in 2005, and then started working at Fraunhofer Research Institute. And actually, my first industrial project partner was Ballard Power System, and so I started working on fuel cell research. And yeah, that unfortunately at this time, anything I show you in the next 20 minutes wasn't there. So we couldn't do all the nice things that I can show you now. And we had but the topic of the project was doing permeability computations and gas diffusion layers. So, but yeah, nothing of what I will show you in the next 20 minutes was available at that time. But we started working on it, and now 20 years later, it can all be done easily in GeoDict, and that's quite nice. So I will show you how to compute relative permeability in a compressed porous transport layer. And yeah, why do we need to compute this value? Just very quickly, you probably all know this. We're looking here at an electrolyzer, and the porous transport layer is a gas diffusion layer or microporous layer, and this has to provide gas and water permeability. It's the same like in a fuel cell. And it has to operate under different saturation levels. So there's oxygen present as a bubble sometimes or not. In a fuel cell, there's the water in a bubble. So it's just the other way around. But it's the same question. And the layer is deformed through the clamping pressure that we have. Yeah? So it's not, if you look at it ex situ on a CT image, it's not the same as if you have built into the electrolyzer or fuel cell. So you have to look at different compression levels. So I will give a presentation here, how to do the structure generation with fiber geo, grain geo, how to apply compression on it, how to do then the single phase flow computation, and last but not least, how to do also the relative permeability. This is two-phase flow computations with GeoDict. And of course, not all computations will be so quick that they fit into the 20 minutes. So I will sometimes load some pre-computed results. So how does such a titanium porous transport layer look like? So if you Google it, that's one of the first hits. It points you to Becker's homepage, and they show you this kind of model here that you see there. And yeah, it consists of some fibers, and that looks like something that we can also do with GeoDict. And if you surf a little bit around on their page, you also get this picture. Looks also like a model. You get also some information of what typical porosities are and thicknesses for such titanium porous transport layers. And also in the internet, you can find micro-CT images done at Paul Institute. They also of this exactly the same fiber type. Yeah, they have fiber diameters between 14 and 50 microns here. So yeah, let's take these values and try to do something in GeoDict that looks fairly familiar. and then do some simulations on it just to demonstrate how it works. So in GeoDict, to make a fiber structure, we have to use FiberGeo. Create fibers. We open that. We choose first some domain size that fits here. I'll do something like 500, 500, 200. So this will be 1 millimeter in the XY and 400 in the thickness. We have to set a solid volume percentage. So the porosity, we take here the 77, so the upper end of what was there on the homepage. And well, we have to say what type of fibers we want to model. We remove the defaults and say, okay, we'll take some curved fibers with some circular cross-section. We have to set a diameter. We take also maybe here the 22 microns. That was the intermediate one there on the on this information. We have to make the fibers longer than the domain size so that they go through the whole domain. And well, one thing we have to set also is if we say we take curved fibers, we have to give some values for the curl. That's a little bit complicated to understand a little bit. We can here decide if the fibers tend to keep the local curvature or the local direction. So if you say they should take a little bit of both, so they don't do a zigzag, but they have to be a little bit smooth curves. And global straightness means if there's some global preferred direction to the orientation, the global orientation of the fiber, or if it's free to, if it bends, it can go in another direction. So that's one of the points where we say if we want to have some anisotropy that we usually have, we have to give it a little bit of a global direction. And if you want to have also it be in plane, we reduce randomness in the Z direction. So you can play around with these values a little bit. There's a little bit something that can be optimized to match a certain realistic structure, but we just take it for now. If we do it for modeling, we should remove the fiber overlap, but it takes some time to do that. So just for the demonstration, I let the fibers overlap with each other. Otherwise, I choose the without overlap, and then the fibers will not overlap in the resulting model. So if I do that and click on generate, just let it generate. And then we'll have the structure here in 2D. I switch to 3D. I have here the structure, and I will improve a little bit here on the visualization so that it shows a little bit nicer. So we have here now a structure, and we can see that fibers are still allowed to overlap here. But yeah, as I said, if I set the checkbox differently, then this overlap will be removed, and the fibers will not overlap, which is more realistic, but it takes a few minutes more to compute. So as these fibers are not only, well, the titanium fibers are actually sintered titanium fibers, and there's one way to model that I actually will shortly show, because I think it's unknown to many that these things exist. There is, in the grain geo, we have here sinter and crystallization, and you can actually use that not to model the sintering process, but to mimic kind of the effect of a sintering process. So it will just shrink the structure, so it keeps kind of the volume, the grammage, but not the volume. Yeah, so that's the effect, and I can set this to a shrinkage, and if I say it should shrink by 10%, it will actually compute for about 40 seconds, and it will, yeah, as I said, it will keep the grammage but reduce the volume, and it will do that by, actually it will keep the same voxel size, but the same amount of voxels, but reduce the voxel length and make all the fibers a little bit thicker and glue together. and then it mimics a little bit the effect of a sintering process. Yeah, you can check this out if it matches to your models. So yeah, you see here, it looks a lot denser here now if I do this the sintering. So if I want to compress this structure later on, because I'm interested in the permeability under compression, because in situ it's compressed, I have to do a compression modeling with ElastoDict. So in ElastoDict offers a number of possibilities, and we have to choose the deformations. And in the deformations, I have to set, oh, this is still solid. This should be the material, should be titanium, of course. Yeah, so I have titanium. Yeah, well, doesn't matter because it's only the this that has some stiffness. And I have to define the load case here. So the experiment, if I want to do compression, is I have to choose compression. Path control is okay. In the boundary conditions to the sides, I have to say it's confined. It's not free. The structure continues. So there's not, I cannot just pass it, and there's free space in all the sides. I have a compression in Z direction, so that's the through plane. And then here I can define the load graph. I can say, okay, the stress goes from 0 to 10, the strain from 0 to 10%. Or I can say, okay, if I want to compress it by 30%, I can decide, okay, I do 30% in 10 steps. And then I have this from 0 to 30 in steps of 3%. And I can do this simulation. So boundary conditions, I shouldn't choose periodic if the structure isn't periodic, because then I get some artifacts. So it's better to have symmetric or mixed, at least. Mixed means that at least in the compression direction, I have it symmetric. And now important also is that in the geometry handling, I select the calculate on deformed geometry. What does this mean? Well, if I do a 3% compression step, then fibers will touch with each other that haven't touched each other before the compression. So I get new contact points. So, and this will increase the stiffness of the material, but only if I take this into account in the next step, that the geometry has actually been deformed and I get new contacts. So if I make this one here, this means that I'll take this into account, because otherwise I just will have a linear stress strain curve, because it's a linear model. And if I'm not calculating on the deformed geometry, I will always calculate the compression step from the original geometry, and I just get a linear output. But if I take this, after this 3% compression, the structure will be resampled. I get new contacts and a stiffer structure as a result of that, and I will get this typical stress strain curve. It will be nonlinear. So that's important here in ElastoDict. And this one, I'm sorry, I can't let it run here. This takes a little bit too long. So I go to the pre-computed results and show what it looks like. So first of all, this was done on a different realization of the structure before the, so this is the structure before the compression. And afterwards, well, I have here the results. You get stress strain results. I can show the plot here. You have here the strain up to 30% in these 3% steps, and you can see that you have this nonlinear increase because you have additional stiffness due to new contacts. So here, under the visualization, you can actually select for all of the steps the deformed geometry, and you can just load it. Yeah. So you have the geometry available. If you load it, it shows the compressed geometry at this this level. And now I can compute things just on this structure. I have it for everything, so I can just compute in GeoDict the flow. And this goes rather quickly. If I just compute the permeability in the Z direction in GeoDict, I can select, okay, it's water maybe in the transport layer. I don't have to change anything here because, yeah, for permeability, the exact pressure drop doesn't matter because I just have the proper, yeah, I just compute this permeability, and this will be the same. And I can leave all the default parameters and just click run and let this run for a while. And while it runs, I show a few slides. I can show the results here in this visualization. In this movie, we can see how the compression compresses this layer, and we see the deformed structure, and on the right-hand side also the von Mises stress on the right half of the structure. So what we can also do is, because the material is not uniformly compressed, because we have this channel rip pattern where it's compressed in between, we can also have a look at this and make a model like this, where we can put some of the rips or whatever pattern we have, and compress it, and then it looks like this. And I think we have seen this image a few times today, and that's because we are actually pretty proud that this now works. It's not so easy as it looks. It was several years of development, and if you would have asked me 20 years ago if such a simulation is possible, I think everybody would have agreed that it's not possible to do that. And yeah, I think sometimes in between, 10 years ago, I think Hyundai asked if can we do that. We said not this year, but next year, and that was a little bit too optimistic. It took a while longer, but now it really works nicely, I think, and just out of the box, and that's great in that case. Yeah, and you can analyze this compressed structure if you, for example, look at it with Math2Market, the 2D density map. You can have a density histogram from the side, and you can see that there's a denser compression under the ribs. And yeah, you could also, if you choose different values, you can choose how big the rasterize it here. Yeah, so you can get some more other statistics there as well. So, but now we have these two things. When should you use what? So, I mean, the left-hand side here, this homogeneous material, this is the one that you should use if you want to determine a function of the material, like the permeability independence on compression rate and saturation rate, because then you need some homogeneous material model where you can compute permeability, and you can compute saturation and compute the function. Yeah, so if you want to have a function for upscaling, you always use this one. You just have then under the channel and under the rib, you have a different local compression, and then you have it in a different position of this function. Yeah? But you still need to compute it from this model. This one you have to use if you're interested in kind of local effects. Yeah? If you want to know what is the compression under the channel at a certain pressure or under the ribs, and what is maybe a flow pathway from here to there under this in this special thing, then you have to look at the complete model with the channel and the ribs and analyze that. Yeah, and now if I switch back and everything works as we hoped for, we are exactly at 100%. Great. And the simulation is finished. And we get the permeability now. What did we do? We computed the permeability for this one compressed structure, and it's written in here. It's for the through plane. We don't have computed the one in the in-plane direction. Of course, if we just make the check marks, we get these values too. So now this is just a single permeability for single compression and fully saturated. Yeah. So if we want to have the results for the unsaturated or the relative permeabilities, we can do that in GeoDict. In GeoDict, we have relative permeability option, and we can, in the relative permeability, we have to choose how the water gas phases should be distributed. So we have here a drainage simulation, and if we're interested in the water phase permeability, so we have air bubbles intruding. So the displaced phase is, in this case, the water, and we can set here at which saturation levels we're interested. So maybe we know already that we don't have too much air in the flow, so we don't need to go from 0 to 1. We can maybe set a certain range that we're interested in. Yeah, I'm not choosing something here. And then here, okay, we have to choose what's invading fluid, what's displaced fluid. So we assume everything's initially filled with water. We have some invading fluid, some air, and yeah, that's set up here. And we have to compute in which direction we're interested in the permeability. So that is through plane again, but of course it could be also interesting to have the in-plane permeability, which would be X and Y. Because also in plane, some permeability is needed because it has to flow somewhere from the under the ribs to the channels, and that goes in plane. So it's not only a through plane flow that happens. Yeah, we set this up, and then yeah, we can compute it, but this also takes too long because it has to do this for all the spots, and also we have to do that for all the compression steps. So we get one result for every of the 10 steps. I can just open them. Link. And so we have here 10 different results. If I select them all, okay, we don't see much, but I can combine them. That's rather nice. If I combine them into one plot, we get, enlarge this, we get some plots here for the I have computed for in-plane and through-plane direction. So for example, for the through-plane direction, we have now here 10 curves. So the red one here is the step 0, is the uncompressed. We have air saturation from 0 to 40%. And then if we go up with the compression level, we move down here. So that's then the function for the 30% compression, and here then up to 40% air saturation. So you could also plot that maybe in 3D. Yeah, so with on the x-axis you have the saturation, on the y-axis the compression, and then on the third dimension the permeability. So you get some kind of this shape, and in this function you could plug into some upscaled model, and you have the behavior of this material under compression and for different saturations. Yeah, and with that I just get back to the talk. And of course, if you have to do this, I use a macro. Yeah, I don't click through all the 10 steps and everything. I just make a macro where I make a for loop from 0 to 10. And in step 0, I take the uncompressed structure, and then I go through these 9 compression levels that I get, and then just always run the same computation on it. Yeah. And then I just collect the results. So that's how you do it. You don't click through all the, because yeah, this way you're also sure that you don't have any differences in the 10 runs, yeah, because it always runs through the same code. So in summary, I've shown you how to generate a 3D structure model of a sintered titanium fiber felt. How, yeah, you can of course vary diameter, porosity, curvature. I just made one quick example of a structure that looks some way realistic. Yeah, it's not some specific structure. I've shown you how you could use GeoDict to mimic sintering. I've shown how you can model in situ compression. You can do that homogeneously or with this flow channel pattern, and then how you can determine transport properties as a function of the local density and local saturation. And of course, you cannot just do that for permeability. You can also do that for diffusivity or conductivity. Now, except that conductivity maybe is not so much from saturation. And yeah, with that, I thank you for your attention.
So hello and welcome also from my side. My name is Arne. I'm Deputy Team Lead of the Consulting and Projects team at Math2Market. And today I'm going to show you the newest features regarding upscaling mercury injection or intrusion capillary pressure in an MPL and GDL compound within a fuel cell. So you might have also noticed that this picture has been shown quite often. I have this picture here in my presentation as an overview of on which part we are looking at in this talk here. And that would be the compound of the microporous layer and the GDL on the cathode side of the fuel cell, which would look like this in GeoDict. So just a short overview what capillary pressure or mercury intrusion capillary pressure is actually. So in principle, you have a high contact angle of the mercury versus the air on a certain material. High means usually higher than 90 degrees. That is then non-wetting. So you would have to apply an external force to force mercury inside of the structure. And based on the force you will obtain a capillary pressure curve, which means that you get the saturation of the mercury as a function of the pressure. And why would we like to do that? We will need the capillary forces, or we would need the knowledge of the capillary forces that are knowledge in the fuel cell to get rid of the water that is in the GDL. So as I was shown before, a compound of a GDL MPL would look like this, where we have on top the gas diffusion layer that is resolved by your microcity or by some structure generator in GeoDict. Then we have a mixture of GDL and MPL, where we have partly resolved parts, the microporous layer and the GDL as well present, and then a homogenized microporous layer on the bottom of the structure. So the question would be here is, how can we obtain the accurate capillary pressure curve across these different scales? We're having the resolved top part of the structure, but we're also having still the unresolved part on the bottom. And the idea is that we would like to combine the information we have from both scales. So this is an upscaling problem here in that case. So first of all, for doing upscaling, we need the function of the capillary pressure curve for the unresolved part of the structure. That can come from experiments where you have solely analyzed the microporous layer, but that can also come from a former GeoDict computation where you have generated a microporous layer, for example, run the capillary pressure command of the GeoDict module, and then you would be able to assign this capillary pressure function to that porous material on this structure, where you can then, by using upscaling, compute the bulk capillary pressure curve. And that would look like this. The mercury first occupies the resolved part of the structure, and when the pressure becomes high enough, it will also start separating the unresolved parts of the structure, because then the capillary pressure is high enough to also saturate these unresolved structures. The GeoApp, or the application, how it was implemented in GeoDict, is rather simple. You can choose from two options of how you would like to populate your porous material inside the GeoDict structure. The first of all would be that you use the powerful constituent material database in GeoDict, and save the pressure and saturation capillary pressure curve directly into the material. So you're having a material, for example, with the name microporous layer, and that material can have certain properties like porosity, density, but also the capillary pressure curve as well. So you assign these parameters to that material, and then you would have that graphical user interface in the GeoApp available, where you choose which would be the result file name, from which side the macro you should invade the structure, and if you upon which saturation you would like your unresolved structure parts to conduct fluids. So there may be a case where you would like to have a microporous layer that does not consist only of one layer of microporous material, but also maybe of two. Let's say you want to have the partly resolved microporous layer with GDL as a material and the homogenized microporous layer as a material. Then you would need a certain saturation which you assign to the upper part of the microporous layer to tell GeoDict upon which saturation that layer should conduct the fluid to the next layer. And that is what you change here in that box. The parallelization is simply how much CPU cores GeoDict will use to perform the computation. The other option would be that you simply load the GDR file that comes out of the GeoDict capillary pressure module. So let's assume you're having you have a microporous layer that was generated in GeoDict. Then you can run the capillary pressure curve command on that structure, which you can then use as an input for this GeoApp to assign the capillary pressure curve to the unresolved material in your structure. And that can be done for up to 3 materials at the moment. The results would look like this. So you would obtain a capillary pressure curve that contains of a resolved part and an unresolved or so-called upscaled part. So in principle, the blue part of the structure consists of the GDL that gets saturated, while the red part consists of the MPL that gets saturated once the pressure reaches a certain level. Based on that, you can, of course, also derive the pore throat diameters of the structure, where you then would have the pore size distribution for the GDL resolved and for the unresolved part also the pore throat diameters. So this is directly copied out from the GeoDict result file of that GeoApp I've shown before. And that can, of course, help you to optimize the MPL and GDL compound, to optimize liquid water removal, or in principle, design better cathode layers here. But what would the GeoApp be without any verification? We have, for the verification, created 2 structures, where we created a structure with a high porosity, or granular structure with high porosity, and one with low porosity. We have now computed on both structure the capillary pressure curve, or macro intrusion capillary pressure curve, so that we would have a homogenized material information for, in that structure here, the left-hand side for the high porosity structure, and for the low porosity structure on the right-hand side. So we simply transferred the information we are having from both structures to the left and to the right-hand side. So each of these 2 areas here have one individual capillary pressure curve that can be upscaled directly from only this structure here. And for sanity check, we have also stitched that structure together into a only resolved structure, where we then run the capillary pressure command on. So the idea was, if capillary pressure curves obtained from both of these 2 structures are looking the same, we know that the upscaling approach works. Yeah, because we are having only resolved structure capillary pressure curves and only non-resolved structures. And as you can see, the match is quite well. Yeah, so for the resolved structure, or the blue curve, we are having an almost identical curve as for the upscaled curve. Only here, at that narrow part of saturation above 90% or around 90%, we are having a small deviation that could be also a boundary effect of this structure here. But that is only the first step. The next step would be to not only compute the capillary pressure curve, but to also compute the relative properties that can be derived from certain saturation levels of that microporous layer and of the gas diffusion layer. And that will be possible in the GeoDict 2025 version in one of the next service packs. So in principle, it is very easy. Principle. You having a saturation, and based on the saturation level, you would like to obtain the, let's say, permeabilities, like Jürgen showed you before. Based on a certain water saturation level, you want to obtain the permeability. That can now also be done if there are porous regions involved. So you're having a two-phase flow that is upscaled, so partly saturated MPL and gas diffusion layers. And based on these partly saturated layers, you can then obtain the relative permeability on the basis of different saturation stages of the water. And as shown before in the MICP Geo app, you can also then use the relative permeability from the unresolved material, and there also from GDR files where you have obtained the relative permeability from the scale below to populate your model on the scale where you have both porous and non-porous materials present. And with that, I would like to close my talk. Thank you.